Welcome to 1.2. Hopefully by this time you have either been a part of the class or seen the video on ELF confusion, and I'm going to speak about that when we have functions. The definition of a function is a little bit tough to get through without that, so highly recommend that video. So we do have our strict definitions of function and characteristics of functions listed here. I do want to go through the summary of function, but ELF confusion takes care of these first couple items, that video. Summary of terminology. If we have a function y equals f of x, f is the name of the function. I would refer to that as a factor. It's the name of our hollowed out tree. We would just say function f. That's what y is. We take x and we put it into f, and that function turns that value into our y value. Okay, so f is the name of the function. Y is the dependent variable, or the output variable. We input x, and y is dependent on the value x. Our factory takes x and takes whatever we put in there and turns it into y. If I'm taking f of my pen, I put my pen in there, and the y value is dependent on the pen. It's the goods that we put into f that get turned into y. So it makes sense that y would be the dependent variable. X is independent. We can choose different values for x, but y is dependent upon what x is. F of x is the value of the function at f. F is the height. It is the y value at x. Okay. So domain are the allowable values for us to put into a function. The range are the possible things that can come out of a function, the possible y values. Implied domain, when we have an algebraic expression, implied domain, you're going to see examples of that. For instance, if I have 3 over x, let's say f of x is 3 divided by x, x may not be 0 because we can't divide by 0. If I have square root of 4 minus x is g of x, let's say, then x could not be 5. 5 is not part of our domain. X can be 4. X can be values that are smaller than 4 as well, but I can't subtract a number bigger than 4 and then take a square root in a real number system. Okay, so testing for functions. This goes back to our ELF confusion video quite a bit. Does the relation describe a function? So all of these values are attempted to be in our domain, and every one of those has to be assigned a value in the range. So negative 1s get turned into 8s every time. 0s gets turned into 6s. 1s get turned into 6s. 2s get turned into 7s. The one sticking point would be, well, how about this? But our ELF in charge of 0s knows exactly what to do with them. Our ELF in charge of 1s knows exactly what to do with them. It's just coincidental that they're both turned into 6s. So is this a function? Yes. Explanation could be each value in the domain is assigned to exactly one element in the range. However, in example 8, our ELF in charge of negative 1s has been told to turn those into 3s, and later on was told to turn them into 4s, so the ELF in charge of negative 1s is confused. And therefore, no, this is not a function because one of the elements in the domain is assigned to more than one element in the range. In example 9, National Football League is assigned to be Giants, but also assigned to be Saints, and also assigned to be Seahawks. Therefore, we don't know exactly what to do with National Football Conference. There's not a single assigned job. This is no. In this case, if we start with Alabama, we know we turn it into a 5, and Alaska gets turned into a 3, and Colorado gets turned into a 9, and Delaware gets turned into a 3, and Nebraska gets turned into a 5. Every element in the domain is assigned exactly one element in the range. Yes, this is a function. This is still part of number 9, obviously, but American Football Conference doesn't know how to be assigned. Okay, in exercise 11 through 14, let me zoom in here a little bit. I need to remember to do that. Make it easy on you to see. In exercise 11 through 14, determine whether the relation represents y as a function of x. So I put in -3 and I get out a -9. I put in -1 and I get out a -1. We put in 0, it turns it into 0. 1s get turned into 1s and 3s get turned into -9s. There is no confusion whatsoever what I do with a -3 or a -1 or a 0 or a 1 or a 3. So determine whether it represents the function. Yes, because each element in the input is assigned exactly one element in the output. However, in number 12, here we've told a 0 to become a -4, and later on we've been told to turn a 0 into a 4. Likewise, a 1 is supposed to be turned into a -2, a 1 is supposed to be turned into a +2. This is not a function. Each element in the domain, like 0, some of the elements in the domain are assigned to more than one element in the range or the output. Okay, on a graph, this is really pretty easy. Here's, for instance, this is the point right here, 3, 4. Here's a point 3, -2. And we would say, well, our elf in charge of 3s wants to turn them into 4s, and our elf in charge of 3s is supposed to turn them into -2s. Therefore, we have elf confusion, and that's where the horizontal line test is so helpful. Here we would have elf confusion. Our elf in charge of 2s doesn't know where to put them. Our elf in charge of 1s doesn't know what to do with them. So horizontal line passes through 2 points. It is not a function. But here, horizontal line hits no more than 1 point on the graph, or vertical line. Holy smokes, I'm thinking ahead a chapter or two. Vertical line test, I'm sorry. Vertical line test hits only 1 point at any given spot on that. And therefore, yes, this is a function. Okay, now, sometimes this can be a little bit tricky. In exercise 15 and 16, which sets of ordered pairs represent a function from A to B? So A, this is our domain. So all elves in charge of 0, 1, 2, and 3 need to produce something from here from them. We don't have to produce all of these things, just something from there. So 0 turns it into a 1, 0 and 1's available. 1 can turn things into -2s because that's part of our output. 2's are allowed to make 0s, and 3's are allowed to make 2's. That's the things that our factories are allowed to make. So is this a function? Yes, because each element in the domain, 0, 1, 2, and 3, are assigned an element in the range. B, 0's can produce -1's, 2's can produce 2's, that's okay. 1's, we're allowed to make -2's. 3's, we're allowed to make 0's. 1's, we're allowed to make 1's. However, we've already told our 1's to become -2. Nope, not a function, because one of the elements in the domain is assigned to 2 values in the range. And here we go. Set A is ABC, set B is 0, 1, 2, 3. A's can be turned into 1's, that's okay. B's, we're allowed to turn B's into 3's. C's can be turned into 2's. C's could be turned into 3's. However, once again, our one element in the domain is assigned to 2 elements in the range. That's what I would define as elf confusion. A's can be turned into 1's, B's can be turned into 2's, C's can be turned into 3's, and it's okay if we don't produce 0's that day. It's okay if we don't turn anything to 0. A, B, and C each have to be assigned to one element. So yes, this is a function. Now 1's into A's, if I just look at this down here without looking up here, 1A, 0A, 2C, 3B, that is a function, but it is a function from B back onto A. A needs to be in the dependent variable position. B needs to be in the dependent variable position. So while this is a function without seeing anything above, this is not a function from A to B. Okay. In exercise 19 through 30, determine whether the equation represents a function of x. Okay, there are graphical ways to do this. If we know what the graph looks like of a function, then we can go back and we can use that vertical line test that we just spoke about. Now, hopefully we know that this is a sideways parabola. This is a parabola. Y squared parabolas look like this. This is a y squared parabola, and it's got a little bit of movement, but it doesn't pass the vertical line test. Now, so this is a no. Algebraically, if we were to solve this for y squared, watch this. I'm going to leave y alone. I'm going to leave it without the squared or the 1. So what did I have to do? I had to subtract 1, and then I would have to take the square root of. Now, if x squared equals 16, hopefully you would say end up saying x equals plus or minus 4. When we take the square root of both sides in equation solving, we have to go plus or minus. So this is plus or minus square root of. And that means if I put a value for x in here, let's say I put in 5, I get y equals plus or minus square root of 5 minus 1, 4. I get y equals plus or minus 2. That means that 5 is being assigned to 2 and 5 is being assigned to be negative 2. So the big key is if we're solving algebraically for y and we have to introduce a plus or minus, it is not a function. Okay. Now, if we know what the square root of x looks like, see the answer so many times in pre-calculus, it lies in the graph. If we know what square root of x looks like, hopefully we know what square root of x plus 5 looks like, and we see that that passes vertical line test anywhere along the way. Yes, this is a function. In solving for y, well, it is solved for y. I don't have to introduce a plus or minus. Hopefully we look at this and we solve for y. We see we just subtract 5. We multiply by negative 1. I don't use a plus or minus. Or hopefully we see this and we just say, well, this is just a plain old line. Appears like the slope might be negative 1 on it. But here, just like in number 20, in solving for y, I'd subtract x, then I would have to take plus or minus square root of, or we realize this is some kind of sideways looking parabola. How about this one? How about if I'm solving this? If I said absolute value of, I'll use r, equals 7, hopefully you would say, well, r can be plus or minus 7. So to solve this, the next step we would say y equals plus or minus, there it is, 3 minus 2x. So whatever value I pick for x becomes two different values, provided that's not 0. So this is a no. Y equals 8. Does that look like this over here, or is it up here? Well, all the values of y are 8. All the values are up 8. So what we have here is a factory that just makes 8. Oops, sorry. That was terrible because it wasn't on your screen. Do that again. I was asking, were all the values over here at 8, or were all the values up here at 8? Y equals 8. They're all up. So what we have, as I just mentioned, is a factory that no matter what we put into it, makes 8s, but that's still a function. Okay, 32. Evaluate the function at each specified value. I want to put 0 in here, so g of 0. G is a factory, and when I teach functions to Algebra 1 students, I would give them a whole list of these, and I would just have them state this. G is a factory that takes things, multiplies them by negative 3, and adds 7. So I just get 7 minus 3 times 0, or 7 minus 0, 7. G of 2/3. Gotta put my glasses on. This is small reading here. G of 7/3. Good thing I did. I get G of 7/3 is 7 minus 3 times 7/3, which is 7 minus 7, or 0. And G of s plus 5. So this is a little bit of a troublemaker for us. What I would see a lot of people answer to this is they would say it must be 7 minus 3s plus 5, and then combine the 7 and the 5 and get negative 3s plus 12 or something like that. But this is just the thing, and G is a factory that puts things right there. So G of s plus 5 equals 7 minus 3 times the thing, and the thing is s plus 5. So I get 7 minus 3s, minus times plus minus, 3 times 5, 15, and we end up with negative 3s. Combine the 7 minus 15, minus 8. Probably a really good time for you to pause the video and try number 38. But I'm going to go ahead with it now. So Q of 2. Q is a factor that takes 2's and puts them here. 2 times 2 squared plus 3 and puts them over, puts the thing t goes here and here. The thing 2 goes there and there. 2 squared, and we get 4 times 2. We do this first. 4 times 2. 2 squared, 4 times 2, 8. We get 11 on 4. And Q, I guess that's a Q. Q of 0 is 2 times 0 squared plus 3 on 0, and that is undefined. And we would ultimately say, hey, 0 is not in the domain. We can't divide by 0. And Q of negative x takes the place of t. So I get 2 times negative x squared plus 3 on negative x squared, which we know is 2x squared plus 3. The negative gets absorbed on x squared. And we can tell that x cannot be 0 here. And that would be Q of negative x. Okay, here is a piecewise function. And for the purposes of this, what we have is we have a factory that takes input and inside treats it 2 different ways depending on the value that comes in. If the value that comes in there is less than or equal to 0, we give it this treatment. If the value is bigger than 0, we give it this treatment. So f of negative 2 being smaller than 0, gets this treatment. So f of negative 2 equals 2 times negative 2 plus 5, or negative 4 plus 5, or 1. F of 0 gets this treatment barely, so it is 2 times 0. It barely qualifies to go out this first chute, or 5. And f of 1 filters down and gets this treatment, 2 minus 1, or 1. And there's a piecewise function. Okay, I'm going to go through the evens of these first, and highly recommend you pause your computer and try the odds. All of these, I believe, are part of the assignment for you to go through again. Domains cause people problems for some reason, and I'm guessing maybe it has something to do with what I've done. But I'm going to make the error of showing you too many of these, because in past years I've seen some problems with this. So the domain is the values that basically won't break the machine. Like if I take my calculator and I try to take the square root of negative 5, my calculator is going to give me an error message. If I take my calculator, let's go through a little bit of that. So I'm going to need to, let's go, for instance, second square root here. If I go negative 5 and I enter that, I get an error. If I go 3 divided by 0, I get an error. If I go sine inverse, there's no reason you necessarily would understand this right now, there I get an error, which tells me that negative 5 is not in the square root domain. And it tells me I can't divide by 0, and it tells me that I can't put 1.6 into whatever this sine inverse thing is. So it's things that would create errors on our calculator. So we'll come back to here, get our focus back in place. So here's all I ask myself is, okay, G is a factor that takes things and puts them here. In order of operations, can I square any number I want? I can square zeros, I can square positives, I can square negatives. Can I multiply any number I want by negative 2? Yes. Can I add 1 to any number I want? Yes. So all real numbers are allowable here. Then 60. Can I multiply any number I want by 3? Yes. Positive, 0, negatives. Can I add 5 to any number I want? Yes. Can I divide any numbers I want? No, I may not divide by 0, so y plus 5 may not be 0. Y cannot be negative 5. That is our domain. It's weird to think of y there because we're usually putting x. So y may not be negative 5. Negative 5 would break the machine. I'd get negative 15 divided by 0. 62, I'm going to use some space down below. Can I square any number I want? Yes. Can I multiply 3 by any number I want? Yes. Can I add any two numbers together that I want? Yes. Can I take an even root of any number I want? No. So down below I'm going to use some space here. In fact, I skipped 56. I'll come back to 56 in just a moment. It's going to be a little bit of a letdown. X squared plus 3x has to be at least 0. So I'm going to test when it is 0. When is x squared plus 3x 0? Well, factor out an x. X times x plus 3 equals 0. And I get x equals 0 and negative 3. So on a number line, negative 3 is of interest and 0 is of interest. Can I put 0 here? I get 0 and 0, 4 through to 0, 0. Yep, 0 is okay. Can I put negative 3 here? I would get positive 9 minus 9, 0. 4 through to 0 is okay. Can I put, for instance, a 1 in here? If I put in 1, I get 1 plus 3, 4. I can take the 4 through to that, so we're good out here. Can I put in negative 1? I would get positive 1 minus 3, negative 2. That's a problem. And can I put in a value to the left of negative 3? You would find we could. So we would say x is less than or equal to negative 3, or x is greater than or equal to 0. Okay. 64. Could I square any number I want? Yes. Can I multiply any number I want by negative 2? Yes. Can I add or subtract any numbers I want? Yes. But I cannot divide by 0. Therefore, in 64, little scratch work over here, 64, x squared minus 2x may not be 0. X times x minus 2 may not be 0. So x may not be 0 or 2. So x cannot be 0 or 2. Okay, 66 has got a couple things going on. Hopefully now our eyes are drawn right here. 6 plus x. So here's where I'm going to put my 66 scratch work. 6 plus x. I can add any number I want, but I can't ultimately divide by 0. Therefore, x cannot be negative 6. That would make the denominator 0. Now the numerator, negative 6 is also an interesting value because it's the limit of what I can put in here. I can put in negative 6, but I couldn't put negative 7 here for x because I'd get square root of a negative. I couldn't put negative 6.1 in here. I could put negative 6 in here, or negative 5.9, but I can't use negative 6 because of the denominator. So my numerator, or excuse me, my number line, negative 6 is off limits, and I can't put negative 7 or negative 8, but I can put values here. So we would say the values we choose for x have to be greater than negative 6. Okay, I'm going to come back up and handle 56, which I inadvertently skipped. And then, again, highly recommend you give 57 through 65 a try, and I'll come back and fill in solutions for those. Okay, 53 through 56, you are to find all the values such that x of x, such that f of x is 0. F of x is 0. I want to know what x value produces a value of 0 there. So f of x is 0, 2x minus 3 times 7. I would multiply both sides by 7. That's still 0 is 2x minus 3. I would add 3 to both sides. 2x equals 3. And I would divide both sides by 2. X equals 3 halves. Oh, not much to that. Some of the problems in that section may be a little bit more challenging. But here's the mistake I used to make. I'd take 0 and put it in for x, but it clearly tells us f of x may be replaced by. Think of equals as may be replaced by. F of x may be replaced by 0. I replace f of x with 0, and we got it. Okay, so this is your opportunity to try 57 through 65. Please pause this, give this a shot. Okay, hopefully I'm just saying welcome back now. May I square any number I want? Yes. May I multiply 5 by any number I want? Yes. May I multiply 2 by any number I want? Yes. May I add any two numbers I want? Yes. And may I subtract 1 from any number? This is all real numbers. That's a perfectly acceptable abbreviation. Okay. May I divide by any number I want? No. I may divide by any positive or any negative number, but I may not divide by t. Therefore, t may not be 0. Okay, sneaky 61. May I subtract 4 from any number I want? Yes. May I take an odd-powered root from any number I want? Yes. We don't have problems with negatives in here. Here we'd have a problem with negatives. We can't have x squared plus 3x be negative. X plus 6 may not be negative. But x minus 4 may be negative because it's to an odd root. So once again, this is all reals. In 63, I may not divide by 0. Therefore, x may not be 0 or negative 2, because if x is negative 2, we've got problems. Okay, and 65, a lot like 66, maybe a little bit easier. I may subtract 10 from any number I want, but I may not take the square root of a negative. So just because of the square root, I'd be tempted to say y has to be greater than or equal to 10. However, if y is 10, the denominator becomes 0, so it can't be equal to 10. So we end up with just y has to be greater than 10. I may add any number I want to 2, and the numerator of a fraction can be any number at once. Okay, 67 to 70, use a graphing utility. So here our first instructions are graphing utility. To graph the function, find the domain and range. So let's take a look. Back to here. I think you may actually see that. That's pretty good. Okay, I'm going to go into y equals and clear out this giant mess. And I'm just going to put square root of x squared plus 1, and I don't usually just hit graph. I usually go zoom, and in this case I'm going to go zoom standard, so I'm just hitting a 6 right now. Zoom 6, and we're supposed to figure out our domain and range. So the domain is the allowable x values, and it seems like this graph's probably going to go on forever. So I believe, based on what I'm seeing here, our domain is all real numbers. And then range, our range looks like it starts to appear at about 1. Now, I could do something like this. I could go second calculate. Let's find that minimum value in here. I move to the left, stamp it, move to the right. And this will give us my smallest y value approximately. And I hit enter, and it says that's at 1. And this is when x equals, that's virtually 0. And I suspect it's probably just a rounding error and truly is 0. So our range goes from 1 up to infinity. So our range would be f of x is greater than or equal to 1. Okay. Then I'm going to talk about interval notation shortly here on these, but I'm going to flip to the back and talk about interval notation, important part of where we're heading in calculus. Okay, and let's take a look at 70. So for 70, I'm going to go back into y equals, clear this. Math, to get an absolute value sign on your TIs, a very easy way to do it is to go to second 0, which is our catalog, because absolute value is going to be early in our alphabetic. There's other ways to find it, but I'm going to go second, and then I'm going to hit catalog. And absolute's the very first choice. Then I'm going to have 3x minus 5. And I'm going to graph that in Zoom Standard. Okay, so it appears like this is going to probably go on to, from the left, it's probably going to go to left forever, right forever. So once again, I believe our domain is all reals, and our range, I think I'm going to find this minimum value. It looks like maybe it's 0 and above. Kind of makes sense that our absolute value might be able to be 0, but I'm going to go ahead and find it anyway. We'll go second, calculate the minimum, ask me for a stamp to the left. I'll get close to it, but stay to the left of that minimum. Whoops, that might be too far over. There we go. Left, hit enter, get to the right of there, hit enter, and now enter. And it tells us that our minimum is occurring at 1.6, looks like repeating with some rounding error. And this, once again, this is times 10 to the negative 6, so this would be 0.000002. It's probably truthfully 0. So our range is g of x is a factory that produces things that are at least equal to 0, and I suspect we can be 0. Okay, now as promised, something new, interval notation. Interval notation is used widely in calculus, and it's really simple once you get used to using it. I'm going to go back to number line days. Let's say we had 3 shaded on forever. You might say this represents x is greater than or equal to 3. In interval notation land, that would be bracket 3, comma, trying to go to infinity. Okay, see if you catch on to this. Let's say we had negative 2 circled and back this way. That would be x is less than or equal, x is less than negative 2. In interval notation, that would be negative infinity. It exists forever until I get to negative 2, but it does not exist at negative 2, parenthesis. All right, let's take a look. Sometimes we get some graphs that look something like this. Let's say we have 5 and 1, circle, circle. And we would say that, let's say this is 1. In regular notation that you might be used to, we'd say x is less than 1 or x is greater than or equal to, nope, just greater than, sorry, greater than 5. In interval notation, we would say negative infinity until we get over to 1, not including 1, or a union symbol, but we don't put the stem on the U. It looks just like that. Or start again at 5, but don't include 5, and go until we get to infinity. All right. Let's take a look at this one. Negative 7 to 3. Let's go dot and circle, shade between. Negative 7 is less than or equal to x, is less than 3. In interval notation, we would go negative 7 including over to 3, not including. Okay. I think kind of a simple way to look at it. The key is we're always going left to right. Where do the values exist? So if we came back to this problem right here, we would say that we would have our range, we would just say is bigger than or equal to 1. So 1 up to infinity is good. Here our range is 0 to infinity. Okay, just want to get that out there because that's a notation you're going to see the book use quite a bit. Here is your assignment from 1.2. I don't believe this one will take too long. Make certain you're asking questions on anything that you're having challenges with. Particularly, we do have people have challenges finding domains and ranges at times. So best of wishes to you, and stay tuned. We'll see you soon.